All right, so today we're going to talk about constitutive modeling. And, who knows what a constitutive model is? So a constitutive model is like it's a closure relation between two variables, right? And you all know one, right? Darcy's law is a constitutive model. It's a closure relation between velocity and pressure or pressure gradient, right? And so we're not really going to solve sort of full-blown momentum balance mechanics problems in this class, in the sense that I showed you the equilibrium or the momentum equation, at least in vector form, is something like this. Right? So in the absence of body forces, it just looks like this. So here you have unknown displacements in the acceleration. So that's rho u double dot. That's accelerations times the divergence of the stress. Okay. Now so far so if we wanted to solve this, what are we going to solve for? We're going to solve for stress or for u. Turns out, that's obviously not enough information to solve this equation. Turns out we actually want to solve for u. We want to solve for the unknown displacements. And so we need a way to relate stress to displacements. Okay? And so the constitutive model is the way you do that. And essentially, we're going to relate stress to strains, and then we'll see that strains are just functions of displacements. So ultimately, we'll be able to write this entire equation in terms of nothing but displacements, unknown displacements, u, and then we can solve that equation. And so the closure relation is the constitutive model. All right? So, you already know one relation from your mechanics course. You know one relation between stress and strain, right? Stress is equal to E times epsilon. What's the name for that guy? Hooke's law, right? Hooke's law. So E is some proportionality constant between stress and strain. And this is in one dimension, of course. But in this course so far, and I know you've seen it in mechanics, but we'll go over it again just for review. In this course so far, we've only talked about stress. We haven't mentioned strain, really. I mean, we certainly haven't talked about it in any kind of detail. So what is strain? What is strain? Change in length over length, right? Exactly. So strain is the final length over the original length divided by the original length, right? Or delta L over LO, okay? And of course, to have a picture, so if I have a bar and I pull on the end of it and I deform the bar, its original length would be LO, its final length LF, okay? So this distance here is delta L, all right? So what about, here we chose to divide by the original length. What if instead of that, what if I chose to divide, what if I had the change in length over the final length? Right? So what if I said instead that strain is equal to LF minus LO over LF. Is that a valid definition of strain? Why not?
Is it being compressed or?
Doesn't matter. The strain can be tension or compression.
Oh, right. But LF is the final, right? The final one?
Why isn't it valid? Because that's not what you were taught in mechanics? What about what if I had the instantaneous length? So I'm pulling on the bar. So the final length is actually changing if I'm continuously pulling on the bar. Right? So what if I had that, in that case, I had the instantaneous length. So I want to divide by the instantaneous length, dl. Now we're talking about a continuous deformation. So the change in length, the numerator is dl. Okay, so like a differential change in length, right? And then I'm going to integrate over the entire deformation process. Is that a valid definition of strain? It's still the same. It's change in length over length. It's just I'm summing up all the differential changes in length. Right? It's as if I'm taking this final length and I'm breaking it up into 100 little pieces and I'm summing up every computation of this. Is this a valid definition of strain? Turns out they're all valid. They're all valid. Okay, and it's sort of the point. I mean, in this class we'll essentially just use this one, but I just want to make a point that it's really important to label your strain. What we typically call strain is actually engineering strain. So it's important to say that this is engineering strain. This guy we'd call true strain or logarithmic strain. And it's, of course, because the solution to this integral, you'd have a log L right there. The reason it's important, so what we normalize it by, I mean, when we use strain, we just want some sort of non-dimensional measure. And so what we choose to normalize it by is sort of arbitrary. You know, we could normalize it by the original length or the final length or the length of that wall over there. It doesn't really matter. Okay? But the reason it's important to label your strain is because if we make a plot of stress strain, say for like 1D, stress versus strain, so far, you know, when you took your mechanics course, you learned that all materials behave like this, right? All materials just behave linearly elastically, right? Do you really believe that? Believe that any material in the world, if I pull on it, the stress is going to be directly a straight line proportional to the strain forever, and then when I let it go, it's going to return to zero strain. Of course that's not true. I mean, we've all bent a paperclip. It doesn't return to its original shape, right? And if you bend it enough, you break it in two, which means you'd have to deviate from this curve somehow, right? So real materials, and we'll see this later in the course, including rocks specifically when they're under confinement pressure, actually have significant nonlinear behavior at large strains, right? So this linear elastic portion is only for very small strains, usually on the order of a fraction of a percent, maybe 1 or 2% at the most strain, right? But most materials, as you continue to deform them, have this nonlinear region, or sometimes you'll hear it called plasticity or inelasticity, okay? And the reason it's important to label your strain is that for very large strains, this difference can be quite large. And something like, it wouldn't be unnecessarily odd to see something like that. And the difference that this is the true strain, and this is the engineering strain. And the reason is specifically, if I were to continue to draw this and this were to say soften, imagine I had a little cylinder. And for the time being, let's just think of a metal, because you could probably visualize this. Okay, so I have a little cylinder, and I'm little pin, you know, of metal, and I'm going to pull on it. Well, at some point, that metal, if the metal's ductile enough, it's going to begin to neck. There's going to be some significant sort of local instability, and the metal will deform like that, right? So it'll neck. This will begin to sort of suck in, right? Well, if you plotted the engineering strain, so engineering strain is just what we wrote there, and engineering stress is the force divided by the original area, right? This area, okay? Well, you'd see this softening behavior because the original area doesn't change, yet when this instability occurs, it actually takes less and less force to cause more deformation. So I don't have to pull as hard. Once I have this local instability, I don't have to pull as hard on my bar to continue to deform it, and you'll see this curve drop off. But the reason you don't see that one drop off is because the true or logarithmic strain would be the force divided by the current area, or the area of the bar in that unstable region, okay? And of course, now, you know, as you're pulling on it, the area is shrinking, and so you don't actually see this fall off. It continues, the material locally continues to essentially get stronger, okay? So we'll talk more later about, you know, specifically about how rocks behave in this nonlinear region, because this is important. I mean, rocks will fail out here somewhere. They don't typically fail over here. They'll fail out here somewhere. And so, you know, if we want to solve wellbore stability problems or something, we need to know a little bit about what's going on out here.